Hi everyone. By this point, we've learned a lot about the derivative. We know what the derivative means, we know what it represents, and we learned a bunch of derivative rules in the previous lesson that help us solve or differentiate a lot of different types of functions. So I hope that after watching that video, I hope that you've done some practice problems, worked on some homework, and that you feel good about just finding derivatives in general. In this video, we're going to start to see some applications of the derivative. All right, let's see what we can do. Okay, so this section is called the derivative as a rate of change. And you might remember that when we first defined the derivative, I did mention that the derivative measures a rate of change. It's the rate of change of the function f of x. So in this section, we're going to explore that a little bit closer and really see what that means. And we're going to see some word problems where the derivative can help us answer some things. So I'd like to start with an example question that's going to seem like we're not really using the derivative at first. But, eventually we'll need to use the derivative pretty soon. All right, so suppose a ball is thrown in the air. And has its height in feet t seconds later, given by f of t equals 40t minus 16t squared. This problem is going to say, find the average velocity for the time period starting at t equals 2 and lasting. There's going to be a few different parts to this. Part A, 0.5 seconds. Part B, 0.1 second. And part C, 0.01 second. Now I'm going to talk us through the answer to this. Let me just give you a minute to make sure you've got the problem down. So this is not like the types of problems that we've answered in the course so far. This is kind of different. So it turns out that we can answer this without calculus. Let's just think about what's happening here. So imagine I don't really have anything like a ball. Just imagine I'm throwing a ball into the air, and we're interested in what's happening t seconds later. In particular, we're interested in a time period starting at t equals 2. So 2 seconds has passed, and then we're going to let some more time pass. So it's almost like we throw a ball into the air. Maybe we have a stopwatch in our other hand. And on the stopwatch, we click the stopwatch to start recording time at t equals 2. And then we're going to measure out a length of time lasting half of a second, and then click the stopwatch again. And each time we could look at the height above the ground of this ball. So the ball goes up, eventually comes back down. All right, part A, what can we do here? Find the average velocity. So this problem didn't really give us velocity. What it gave us is a formula for height. And what I'd like you to think about is, what is velocity? Velocity is how fast an object is moving, right? It's how many feet per second this object is moving. Or really, how many feet per second the height is changing. So we could measure the average velocity over this period of time by thinking of the change in f of t divided by the change in t. That would give me the average velocity because it's divided by the change in t. You know that velocity is going to be measured in something like feet per second. So the numerator is going to give us feet. The denominator is going to give us seconds. So it's going to be feet per second. Anyway, what's the change in f of t over this time period? So the time starts at t equals 2, and then it lasts 0.5 seconds. So it's going to go from 2 to 2.5. So we could say the change in f of t is f of 2.5 minus f of 2. And then the change in t is how much time has passed. How much time has passed? Well, that would be what's given, 0.5. So if we could figure out what this equals, that's going to be the answer. F of 2.5, so we could put 2.5 into this formula that's given, see what we get. We could put 2 into this formula that's given and see what we get. I'm going to tell you to save a little bit of time here that I worked this out, and I found that this equals negative 32. And I'm going to label it as feet per second. Okay? The next part of the problem wants us to do the same thing, but it's a different interval of time. It also starts at t equals 2, but this time it only lasts 1/10 of a second. So this time we want the change in f of t over the change in t. So maybe we could write f of 2.1 minus f of 2 over the length of time is only 0.1 this time. And again, you could put in 2.1 into the original function, put in 2 to the original function. Now we're getting some things in here like 2.1. We're getting some messy decimals in here, so I might have used a calculator to find this. I wound up finding minus 25.6 feet per second. So different length of time, different average velocity. One more. Look what's happening here with this last one. So we threw the ball in the air, and then at the 2-second mark, we have our stopwatch in our hand. We click it, right? And then 1/100th of a second later, we click the stopwatch again. It's sort of like we're measuring the height at t equals 2, and then we're measuring the height again only 1/100th of a second later. It's very, very close. Can you even click a stopwatch that quickly? Probably not. I don't think I could. All right. This is going to be this formula, and I wind up getting negative 24.16 feet per second. Let's talk about this a little bit. This looks different from the problems we've been doing over the past couple of sections. And really, this is something that could probably be discussed in an algebra class too. I mean, you know, we talk about slope, and it kind of looks like we're doing slope, doesn't it? Anyway, some remarks about this. Remarks, we're using f of t plus h minus f of t over h, where h equals 0.5, 0.1, or 0.01. The problem was set up that way, where that's what we had to do. It almost looks like we're letting h approach 0. Problem didn't really tell us to do that, but it was definitely letting h get very, very small. And I'm going to tell you that as h approaches 0, if we were to actually do the limit and let h approach 0, the velocity, meaning the answer that we get, it approaches negative 24 feet per second. We call this the instantaneous velocity at t equals 2. And now we understand that this is really the derivative, right? Because we would take that expression f of t plus h minus f of t over h, take that expression and you let h go to 0, that looks awfully a lot like the formula for f prime of t. That's why we waited until now to discuss this, because now we understand the derivative. And in general, we are going to say f prime of t measures the instantaneous rate of change of f at t. Maybe it's velocity. If f is a function that's measuring something like height or distance, then f prime would measure velocity. But if f is a function that measures something else, we could still say f prime is measuring the instantaneous rate of change of the function. Here, let me show you something. That negative 24, how did I actually get that? I'll show you how I got it. The formula that we were given in that word problem above was this: 40t minus 16t squared, okay? What if I find the derivative of it? We could find the derivative of this very fast. Now, the only thing that's different now compared to the previous lesson is that we don't have any x's. That's okay. Instead of a variable called x, we have a variable called t. All of the same rules still apply. You might have to just kind of shift your thinking a little bit, apply the rules with t's instead of x's. But the derivative of 40t is going to be 40. The derivative of 16t squared, the 2 is going to come down out front, 32t. 2 came down and got multiplied by the 16. And what does this have to do with the answer that we got above? If I find f prime of 2, because that was the t value of interest, the t value that we were interested in, put in 2, and you get 40 minus 32 times 2, and you get negative 24. That's how I got the negative 24 that I wrote up above. So, it looks like we're able to do this without writing the difference quotient and without writing the limit as h goes to 0. And the earlier way that we kind of talked about average velocity over a length of time, that's fine if you want to know the average velocity over a length of time. But if you want to know the instantaneous velocity at t equals 2, that's what this is. The instantaneous velocity at t equals 2. So 2 seconds after the ball was thrown in the air. Okay? Throw a ball in the air. 2 seconds later, how fast is it going? At that exact moment in time. Not over some long interval of time lasting half a second or lasting 0.1 seconds or anything like that. But just at that specific moment in time, what's the velocity of the ball? Negative 24. Maybe I'll just say this as kind of a side note. Why are all these answers negative? Why are all these answers negative? Well, the height of the ball seems like it's measured by f of t. We found a negative rate of change for the height of the ball. So what happens is that means that the height of the ball above the ground is decreasing, right? If you think of it in terms of slope, a positive slope means something is increasing, a negative slope means something is decreasing, as you kind of look at a graph from left to right. So basically, the ball is already on its way down. We threw the ball into the air, and it's already falling towards the floor. That's why we got a negative answer. Oh, you know what? Here, side note. Just thought of this. What about at t equals 1? So, let's say you throw the ball in the air, and now I'm going to measure the instantaneous velocity at t equals 1. In that case, you do f prime of 1. It's still the same f prime of t, except this time I'm putting in t value of 1. So I would get 8 feet per second here. And that's a positive 8. So the thing that I wanted to show you here is 1 second after the ball is thrown, its velocity is 8 feet per second, and it's a positive 8, which means the ball is still going up. By the time we get to 2 seconds in, we have a negative velocity. The ball is already on the way down. There's some moment in between t equals 1 and t equals 2 where that switch must have occurred. All right, let me give you some definitions here. We want to be able to look at other problems besides just this one. So, definitions. If an object's position, which is sometimes known as displacement, at time t is f of t, then we're going to say velocity. Really, in parentheses, I'll say that what we're talking about is instantaneous velocity. Instantaneous velocity is given by what do you think I'm going to say here? Do we need a big formula? I'm going to say velocity. Let's call it v. The velocity at time t is simply the derivative of f, so f prime of t. So if we're given a function f of t that measures the position of an object, and when I say position, it might be something like the height above the ground, or it might be how far along we are on a racetrack, just something about where the object is located, the object's location at time t. Then you take the derivative of it, that gives you the velocity at that moment. So it's the instantaneous velocity at that t value. You know what? I'm gonna throw something in here that What about speed? What is speed? Speed is something that we're actually not going to talk about much, but you might be wondering, is velocity the same thing as speed? Well, let's look at this. In this example above, we saw that sometimes velocity is positive and sometimes velocity is negative. What about when you're driving? Okay, you're driving your car, you look at the speedometer. You look at the speedometer at a specific moment in time. At that moment, you want to know how fast are you going. You don't want to know what's my average velocity over some long period of time, right? You want to know, like, right now, right at this second, what's my velocity. And or I used the word velocity, but maybe we're talking about speed. Okay, here's what I'm getting at. When you drive your car forward, your speedometer says you're going, 30 miles per hour or something. If you put your car into reverse and you drive in reverse, does the speedometer go negative? No, no, the speedometer still shows you a positive value. You'll be driving in reverse, you look at the speedometer, and it'll say 10 miles per hour. So it seems that even though you're going in the opposite direction, it's always positive. That is what we mean by speed. So speed is always positive or zero, and it is the absolute value of velocity. So we could say speed is the absolute value of v of t, which is the absolute value of f prime of t. I'm going to put this whole thing in parentheses, this whole thing about speed, because I don't think we're going to need it much. In this class, we're going to be focused more on velocity. I just thought I would address this. What's the difference between velocity and speed? The difference is that velocity can be positive or negative. And if velocity is negative, that indicates direction. You're going in the positive direction or the negative direction. It might be forward and backwards. It might be upward and downward. So in a way, velocity kind of gives us more information. Speed is something that's commonly used in real life when you're driving or flying or whatever. And it's not really concerned with direction. It just wants to know the number. And it just uses absolute value to turn the negative ones into positive ones. Okay. We are going to focus more on velocity. That's why I put speed in parentheses. The next definition, put a star here. The rate at which an object's velocity changes is called acceleration. Let's underline that. Oh, well, this is the rate of change of a rate of change, isn't it? Because velocity is already a rate of change, and now we want to know how fast is that changing. So, maybe I throw a ball up into the air, or maybe I'm driving or whatever, but at some specific moment in time, maybe I might want to know the velocity of the object and what is the acceleration of the object. It's the rate of change of velocity. We could call it a of t. So far, we had f of t for the location, displacement, position, whatever you want to call it. We had v of t for velocity. And now a of t is the derivative of velocity, which would be the second derivative of f. All right, cool. So that means that there is an actual use for the second derivative here. I'm going to summarize some of this. Key idea. If you have the position of an object and you want to know its velocity or its acceleration, Let's talk about how these three things are related. We can go from position to velocity and from velocity to acceleration. And the way you do that is you differentiate. Differentiate, differentiate. So if you can remember this, this is going to be pretty helpful for word problems. All right, pretty cool. So some word problems are going to give us some information about the position of an object. It might ask us a question about the velocity of the object, or it might ask us a question about the acceleration of the object. And you need to differentiate once or maybe twice, depending on what the problem is. So I'm going to show you a word problem that I'll talk us through. After this word problem, I'll probably give you a separate one to try yourself. All right, a dynamite blast. Blows a heavy rock straight up. With a launch velocity of 160 feet per second. Its height above the ground is S equals 160t minus 16t squared after t seconds. There are going to be a few questions about this. Part A, how high does the rock go? Part B, what is the acceleration at t equals 1 second? And part C, when does the rock land? So I'm going to give you a minute to make sure you see all of this, but I'm going to talk us through this problem. So the problems in this section tend to be unique. They tend to all be different from each other. The first thing I looked at earlier was something about a ball being thrown in the air. Maybe you could say that this is not really all that different. Dynamite blast blows a heavy rock straight up into the air. It's going to go up and eventually it's going to fall back down, right? But it's still kind of a unique question because look what it's asking us. How high does the rock go? When does the rock land? I mean, those seem like those could be useful things to find. So let's get started on this. Solution. Part A, we are given S equals 160t minus 16t squared. And, we sometimes use the word position. We sometimes use the word displacement. In physics, S is often used for displacement of an object. And this is a function of t. If we'd like to, we could think of S as S of t, like a function. All right? Now, what do we know about this function? What do we know? Well, it's a parabola. I can tell that by looking at the formula, right? Because it's quadratic. Highest power of t is t squared. I can tell that it opens downward because the coefficient in front of t squared is a negative 16. So I guess if we were to graph this, and I'm not even necessarily drawing like an accurate graph, I just want a quick sketch. I guess the variable is t, so the horizontal axis would be the t-axis. A parabola that opens downward, like that. Does that make sense? Yeah, I think that makes sense, because if this rock gets blasted up into the air, it goes up and up and up and up and up. Eventually, it reaches some maximum height, and then it starts falling down, 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 down. This part of the problem is asking us, how high does the rock go? What is the maximum height? So this moment here, there is a maximum. So the trick to do this, there's more than one way to do this probably, but the trick that I'm going to use is I'm going to notice that at the peak, at the highest height, it looks like the slope of the tangent line would be 0. Slope, 0. So I think the derivative of it would be 0. In other words, the max height is when the velocity is 0. Does that sentence make sense? So we have a rock, it's going up. Maybe at first we were told the launch velocity is 160 feet per second. So at first it's going, in that first second, it goes very far, very fast. But then, the pull of gravity makes it want to come back down, and the rock is, the velocity is getting lower and lower. At the peak, for that one moment, the velocity is going to be 0. And we're seeing that as a horizontal tangent line. And then after that, the height goes negative. The height starts dropping. The velocity becomes negative. All right, because it's going downward, it's decreasing. Let's just do this. V of t is supposed to be s prime of t, right? We can do the derivative of this function, 160 minus 32t. I did that derivative very quickly, but if you need to write more work for that, that's fine. We broke that into the rules from the previous lesson. Derivative of this, derivative of this. The variable is just called t instead of x. When does this velocity equal 0? Set it equal to 0 and we'll find out. I put a right-hand side and I set it equals 0. From here, can I solve for t? Yeah. I get t equals, let's see, negative 160 over 32 is positive 160. All right. Negative 160 over negative 32 is positive 160 over positive 32. So this equals 5 seconds. Did we answer the question? No, we didn't answer the question. It's asking how high does the rock go? You don't say how high does it go 5 seconds. That's a length of time. But however, what we did just find is we found that the maximum height occurs 5 seconds in. 5 seconds into this trajectory, the rock is at the highest point. So at t equals 5, what is the height? If we can answer that, then we'll have the answer to part A. This is the easy part. This is the easy part. We have a formula given to us in the problem for the height. All I have to do is put in 5. S of 5 is 160 times 5 minus 16 times 5 squared. Whatever this winds up equaling, that's going to be the answer. So this is 800 minus 16 times 25. We don't need a calculator for this. 16 times 25 is 400. So 800 minus 400 is 400 feet. That is the maximum height. As kind of a bonus, we found out that that maximum height happens 5 seconds in. So we found what it was asking for, and furthermore, we found how long it takes for that to happen. So you imagine this heavy rock or boulder or whatever it is, it just got blasted up into the air 400 feet. That's pretty high. There were two other parts to this problem. You know what? We could do part B right here. Part B is going to be very quick. Part B says, what is the acceleration at t equals 1 second? Acceleration is supposed to be the derivative of velocity, right? We already found velocity. V of t is 160 minus 32t. So I want to differentiate. I'm going to underline this part. This is v of t, right? V of t is this. We want to differentiate that. So the derivative of 160, that's a constant. So the derivative of 160 is 0. The derivative of minus 32t is minus 32. There's no t's or anything like that. We just got a formula for the acceleration. We said the acceleration at time t is negative 32. That is going to be the answer. Technically, we could say it is measured in feet per second squared. And you might say, wait a second, this problem asked us for the acceleration at t equals 1. And it seems like I didn't even use the t equals 1. Well, that's true. But that's because I noticed that if I did put 1 in, v prime of 1, I'm going to get negative 32 because no matter what value you put in, this looks like it's always negative 32. So yeah, the acceleration at 1 second is negative 32. By the way, the acceleration at 2 seconds, at 3 seconds, at 4 seconds, 5 seconds is also negative 32. Because the acceleration is not changing. The velocity is changing, but the acceleration is not. What is causing this rock to accelerate? Well, it's gravity. Gravity is what's causing this rock to accelerate, and the negative 32 feet per second squared, that is the force of gravity basically making the rock come back down towards the ground. Whether the rock is going up or whether the rock is going down, either way, it's feeling the effects of gravity, and that is going to be constant. Gravity is a constant. Maybe if we were doing this experiment on like a different planet, you'd get a different number here for, a different gravitational pull, but it would probably still be constant. We have one more part. So part B was quick. One more part. So, look up in your notes, what did part C ask us? It says, when does the rock land? I'm going to quickly reference that little picture we had, or I guess let's just draw it again. We had this, boom. T, S. All right, I want to say that the rock lands when S of t is 0. S of t is supposed to be the height above the ground, and I think we could safely say that the rock has landed if the height above the ground is 0. So let's take S of t. There's 160t minus 16 squared, and let's say it equals 0. And let's just solve for t. Solve for t, because this question was asking us when. Now, everything in this problem was measured in feet and seconds, so I think if we solve this for t, we're going to get some number of seconds. 160t minus 16t squared. This is just an algebra problem now. I think I would factor out 16t. Make it look like this. Looks like we're getting two answers. T equals 0 and t equals 10. Does it make sense that we got two answers? Well, yeah, you know, the rock is at a height of 0 at t equals 0, because at t equals 0, that's the moment when the dynamite blast happens, and then the rock starts going upward. So at that moment, it is on the ground. And we just found that 10 seconds later, it's back on the ground. So in the context of this problem, it said, when does the rock land? So I am only going to circle the 10. When does the rock land? 10 seconds after it was launched. So we don't say that it has landed at 0 seconds. Didn't even lift off yet. So sometimes you have to do a reality check and ask yourself which answer is the one that it's really asking for. I would also add, as a side note, I think that you could also probably argue that this has to be 10 seconds because this was 5 seconds. At 5 seconds in, the rock was at its peak. By the way, that peak was at 400 feet. So 5 seconds in, you know, let's label some more of this. Here's 0 seconds, right? 0 seconds in, it's on the ground. 5 seconds in, it reaches the max. 5 seconds more, and it hits the ground. Why is it 5 seconds more? It's because this parabola is supposed to be symmetrical. If it took 5 seconds to go up, it's going to take 5 seconds to go down. So you could argue, you could do this, and you could kind of take that as a shortcut if you really wanted to. But I would caution you that that only works because this is a parabola, and in some other problems, it might not be a parabola. You might not have that kind of symmetry. All right, so we answered 3 problems, kind of unique, but we did use the derivative. The derivative we solved wasn't really that hard. I don't think it was the hardest derivative we've done. I think the hard part of problems like this is just figuring out, what is it asking me? What information is it giving me? What do I need to set up? But the actual algebra and actual calculus we did, I think, wasn't really that hard. All right, I have one for you to try. This problem I give you is just going to have one part. It's not going to be like a part A, B, C. So, example. A cannonball is dropped from the Tower of Pisa, 180 feet above the ground. During its fall, the cannonball's height above the ground is S equals 180 minus 16t squared after t seconds. What is the velocity at the moment of impact? Okay, so I'd like you to pause the video and give this problem a try. Might take a few minutes, and then you could check back with me and I'll go over this. So this time, instead of having like a ball that gets thrown up into the air or a rock that gets launched up into the air, we have something that's just getting dropped. So there's no going up and then going down. This thing is just falling. How about this? Sometimes in these problems, because I know we're dealing with, displacement, velocity, acceleration, sometimes it's useful to just write all three of them right away. So we were given this one. That's the height above the ground, also known as position or displacement. Let's just go ahead and find velocity is the derivative of this. So we could take the derivative pretty quickly by now, right? This is negative 32t. And I'm going to go ahead and find the acceleration just in case we need it. The acceleration would be the derivative of v, so negative 32. All right, we have all those off to the side. We'll use whichever ones we need. So when do we think the impact happens? I guess you could say that this is similar to part C of the previous problem that was asking when does the rock land. The moment of impact is going to be when the cannonball lands. So how about we use this and say that the impact happens when 180 minus 16t squared equals 0, because that's going to be when the height above the ground is 0. Can we solve for t from this? Well, let's try. Let's see what happens. This is just algebra. 16t squared equals 180. Divide both sides by 16. You get t squared is 180 over 16. That simplifies to 45 over 4. The way that I'm thinking about this is, the problem says the cannonball's height above the ground is this formula after t seconds. So the idea is, again, I kind of imagine it as like a stopwatch. You drop the cannonball, and when you drop the cannonball, you start a timer on a stopwatch, and starts counting up from 0. That's what t is. Can we get t from this? I'm going to say that when we take the square root of both sides, we would expect to usually do a plus or minus symbol, right? When you do a square root of both sides of something, you do a plus or minus. Because this is a real life problem, because this is like a word problem and it actually means something, I'm going to think about it. I'm going to say that I don't think that t could be negative. I don't think that a negative value of t is what we're looking for. So I'm not going to write the plus or minus symbol. I'm just going to say positive square root 45 over 4. It's kind of like in the previous problem when we got t equals 0 and t equals 10, and we said that only t equals 10 made sense as the answer. A negative value of t, I don't think that the cannonball is going to impact the ground before we drop it. The cannonball is going to impact the ground after some positive amount of time has elapsed. So, square root of 45 over 4, can we clean this up at all? I guess we could say it's the square root of 45 over the square root of 4, get the square root onto each part. The nice thing about that is I know the square root of 4 is 2, so maybe we want to write it this way. And if you remember how to simplify square roots, you'd say 45 can probably be broken up. Like, make that 45 9 times 5. And then you say, we know the square root of 9. The square root of 9 is 3. And that could be a 3 over 2 square root of 5. So what did we just find? We found the t-value of when the impact happens. After this many seconds, whatever this number is, after that many seconds, the cannonball hits the ground. But the question is asking me, what is the velocity at the moment of impact? So let's find the velocity at this moment. We know the t-value. All we have to do is put it into v. So now I'm glad that we went ahead and we found S, V, and A. It looks like we're probably not going to need A after all, but it only took a second to find it. Yeah, V of this is going to be the velocity at the moment of impact. So V is supposed to be negative 32t. This is the t value that we found. So we get negative 32 times 3 over 2 square root of 5. Okay, can we simplify that at all? A little bit. Negative 32 times 3 halves is going to get you negative 48. So you could say negative 48 square root of 5, put a box around it, that many feet per second. That's going to be the velocity. I was expecting that this answer would be negative because the height above the ground is decreasing. So that part makes sense. I guess if you ask me what is the speed, then I would just turn this into a positive. But we're not going to talk about speed very much. All right, so that's the answer. Negative 48 square root of 5. Now, should we find this as a decimal? Well, you know that at the beginning of the semester, I said we weren't really going to use calculators much in this course. This is a calculus course that's designed to not use calculators much. So I'm happy with this answer the way that it is. If you are curious, I'm going to tell you what it is as a decimal. But I'm leaving the box around the negative 48 square root of 5 because I like that answer. This is approximately equal to negative 107.3 feet per second, which is pretty fast. I would not want to get hit by a cannonball traveling at that velocity. You imagine traveling about 100 feet per second. Okay. Okay, so that was our section on the derivative as a rate of change. We will continue to talk about the derivative as a rate of change throughout the course, but I think what we've seen here is mostly problems that involve location, velocity, and acceleration. And if there's one big thing that I'd like you to take away from this section, it's this key idea that I wrote down. It's this stuff, okay? This key idea that I wrote down in the middle about position, velocity, acceleration. How do you go from one to the other? You differentiate. Okay, that is going to be important because really to answer a lot of these word problems, that's the calculus that you need to know. You need to know that you go from position to velocity to acceleration by differentiating once or differentiating again if needed, if the question involves acceleration. Other than that, it's the usual kinds of word problem skills, which you've seen in algebra classes and pre-calculus classes. You know, the general advice, like be extra careful when you read a word problem to make sure that you understand what information is given, what information is it asking for. When you get your final answer, you could take a step back and double check to make sure that you really answered what it was asking. All of that usual stuff about word problems. Okay, so word problems with this little calculus twist where we're doing some derivatives. What else can I say about it? here's something as just kind of a final thought before we go. This picture, this diagram that I drew, you might be wondering, I don't know if anybody thought about this, but you go from position to velocity by differentiating. You go from velocity to acceleration by differentiating. Here's a question. Is there a way to go back up? Is there a way to go backwards? Like, what if I was given velocity and I wanted to know something about position? Is there a way to do that? It feels like we would need to do something that's kind of like the opposite of the derivative. That's coming later in the course. All right, so later in the course, we will have that kind of diagram, but we will be able to take the arrows and also have a different kind of arrow pointing upward, which is pretty useful if you know something about your velocity. Maybe because you are in a car and you look at the speedometer and it tells you how fast you're going. You know something about your velocity. What if you want to know something about your position? So we'll get to that kind of stuff later. So what are we doing in the next upcoming videos? So this video was some word problems. The previous videos were about the derivative and solving derivatives. Now we talked about word problems. The next videos are going to get back to just methods for differentiating functions, because it turns out that there are still a lot of functions that we don't know how to differentiate yet. So the next few videos are going to be pretty important, where we're going to learn how to differentiate a whole variety of functions, trig functions, exponential functions, logarithmic functions, different types of functions that are multiplied times each other, different types of functions that appear as a quotient, right? Like, what if you had a polynomial over a polynomial? We need new derivative rules to handle all of those situations. So that's what the next few sections are going to be about. All right, so I've been talking for a few minutes here. Why don't we stop? So thanks for watching, and I'll see you next time.